Hello, and welcome to Lecture 4 of Changing Magnetic Fields in PHYS 1204. In the last few lectures, we've seen some little hints that changing B fields result in electric fields, and also some hints that these electric fields are somehow different from the electric fields we've seen before. So now we're going to take a closer look at them. We've already seen that for a loop of wire in an increasing B field, like in this picture, there will be a current induced. But these are non-moving charges inside the wire, and so they don't feel magnetic forces. It isn't that B field that's causing them to start moving so that there's a current in the loop. So there must be electric forces acting on the charges in the wire, which cause the current to flow. And where there are electric forces, that means there must be an electric field. So we can conclude that this changing magnetic field produces an electric field. But what's the shape of that field? Well, the fact that it gets current going around a loop gives us a hint that it can be a circular field. Now, it isn't always circular. If the region containing this increasing B field is cylindrical, so it has cylindrical symmetry, then the E field that it produces will also have cylindrical symmetry, and so it will be circular loops. But whether it's circular or not, it always forms closed loops. One reason for that is that there are no isolated charge carriers here for the field lines to terminate on in the way we've usually seen field lines do. There are some important consequences of the fact that these E fields that are induced by changing magnetic fields form closed loops. So let's think about the work done on a positive charge as we carry it from this point A to this point B. Here's what we've seen previously in the course for how we can calculate this work. And clearly here the electric force on the charge is going to be in the direction of motion the whole way along the path, and so this will be a positive work. But now think of going around this different path too, from A to B. Everywhere along this path, the electric force is opposite the direction of motion, and so clearly this will result in a negative work. And so the work by path 1 and the work by path 2 are clearly different. This is different from what we've seen for E fields previously, because for the E fields we're used to, the work done by those fields is path independent. Well, we've already seen this because we've been talking about work done by EMFs, and all we're doing here is writing that down in a different way. So these two works are not the same. The work done by induced electric fields is path dependent. Well, around a closed path, then, that means you have a non-zero work, which is also different from what we've seen for E fields before, right? The fact that the work done by an E field around a closed path is zero normally is just another way of thinking of Kirchhoff's law, but that doesn't apply to work by these induced electric fields. So now we can take our work per unit charge, which is our induced EMF, and we know from Faraday's law that that is related to the rate of change of magnetic flux. That gives us this, which is an alternate form of Faraday's law, but for our purposes the reason it's useful is that it gives us a way of calculating the electric fields that are induced by changing magnetic fields. So what we're seeing here is that we have two kinds of sources for electric fields, and they result in fields with fundamentally different properties. We've seen that when the source of a field is a charge, we get what we call electrostatic fields, whereas induced electric fields are produced by changing magnetic fields. The work by electrostatic electric fields is path independent, but the work by induced electric fields is path dependent. And for electrostatic electric fields, the E field lines always terminate on charges. They come out of positive charges and go into negative charges. But for induced electric fields, they're not produced by charges, and so they don't terminate on charges. The lines form closed loops. Both of them are unified by the same overall definition of the E field. In both cases, this is obtainable as an electric force divided by the charge on a probe charge. But for electrostatic E fields, there are other ways we can calculate it. If we have a set of point charges producing the electrostatic field, then we can calculate it this way, or using an integral for a continuous charge distribution. We also know that we can get it from Gauss's law, and we also know that if we've previously found the potential in some way, then appropriate derivatives will get the components of the E field. But that's only for electrostatic E fields. For induced electric fields, what we have is this new form of Faraday's law as a way of getting it. And in particular, the more familiar ways, this way or Gauss's law, won't work for induced electric fields because they aren't produced by charges. And in particular, because the work is path-dependent, there's no connection between induced electric fields and any position function v, and so you cannot get induced electric fields from potentials. How strong are these electric fields that we produce by changing B fields? Well, let's look at a fairly doable situation. We know that with a solenoid, we can generate a B field of about 10 to the negative 2 Tesla. And so if we have a big beefy solenoid and we're cranking up the current in it so that the current is changing, we should be able to achieve a rate of increase of the B field of about 0.01 Tesla per second. That should be quite achievable in the lab. So let's find the E field strength that would result 1 centimeter away from the middle of the solenoid. Well, we're going to have to define an Amperian path. The whole situation has cylindrical symmetry. The region of space where there is a B field is cylindrical. So the E fields must also be cylindrical in their symmetry, and we've already seen that they make circles. And if you think about Lenz's law, it will tell you that the E fields are going to point around this way. That's what the negative sign here is saying. Well, so I am going to define my dA, my area elements for this flux, to be out of the page, and so that's going to make this flux come out positive, and so the rate of change of flux is going to be positive, and then that means I have to trace my path around this way for everything to work out, so that now my dot product between E and dl is negative, as it should be. With that, my E field is parallel to my dl vectors everywhere. It's actually anti-parallel in exactly the opposite direction, and so E dot dl is negative E dl. And so Faraday's law now looks like this. The negatives cancel. The E field is uniform everywhere on this Amperian path by symmetry, and so I can just pull it out. And as I hope is becoming familiar, that means I now have a nice, easy integral that is nothing more than the length of the path, which is going to be the circumference of the circle. This magnetic flux is due to a uniform field, and so it's just going to be the B field times the area of the circle here. And I know that that area of the circle isn't changing, and so it's just the area dB by dt. That area is just pi r squared. And I know dB by dt, it's 0.01 Teslas per second. I'm just going to leave it as dB by dt for now. And so there we have it. There's a whole bunch of cancellation. Pi's cancel, 1 factor of r cancels. So our final answer for our E field strength is just R over 2 dB by dt. This R was 10 to the negative 2 meters. This dB by dt was 10 to the negative 2 teslas per second. You can verify that that comes out to the correct units, and it is 5 times 10 to the negative 5 newtons per coulomb, which is much weaker than we're used to seeing due to things like charged rods. But also notice it's proportional to R. The E field gets stronger as we get farther away from the center of the solenoid. There's an important and useful consequence of Faraday's law that we'll look much more at in the next video lecture. Let's suppose we have a battery, and there's current running, and it's going through this small resistor and then through a solenoid. Now we switch so that instead of the current running through the small resistor, it goes through this larger resistor. Well, the current will decrease. However, there is a magnetic flux through the solenoid, and since the current through the solenoid is decreasing, the B field in it is getting weaker. That generates E fields, and those E fields result in an EMF that acts just like the solenoid was a battery oriented this way. In other words, they tend to keep the current going and reduce the rate at which the current decreases. If you think about what's going on with these induced electric fields, you'll realize there's something rather strange going on. Let's think about a situation where we have a wire loop, and there's a region in the middle of the loop where we're making the B field increase. So perhaps there's a solenoid that's just in there, so the solenoid has a much smaller radius than the wire loop that we're thinking of. And the B field outside that long solenoid is approximately 0. So, to a good approximation at least, we are only changing the B field at the very middle of the loop of wire. And yet, because we know that the flux through the wire loop is changing, we know there will be a current induced. Well, you might ask yourself how that's true. The B field is 0 and is unchanging, where the actual electrons are in the wire, and surely we're talking about an interaction between this changing magnetic field and the electrons. And so, how do the electrons even know that the B field changed in the middle of the loop? Well, realize that, again, it's not the B field that's inducing the current. It's the electric field that results from the change in the B field. And this form of Faraday's law tells you that the E field is induced everywhere in this region, not just in the place where the B field is changing. There will be E fields all through this region. What we've just seen is that if the B field changes anywhere, then the E field will change everywhere. Well, the story doesn't end there, because there's a more full version of an equation we've already seen. And we don't really have time to get into this, I'm just showing it to you briefly. So here's an equation we've already seen. This piece right here is Ampere's law. But it turns out it's missing a piece. There's a piece we don't have time to look at except for right now, which is right here. And this is telling us that when the electric flux changes, that produces a B field. So if these B fields are producing changing E fields, those E fields will in turn produce B fields, which are changing, and so they'll produce E fields, which will produce B fields, and on and on and on. And the whole process propagates outward, propagates like a wave. Well, here's something sort of interesting. If you look at 1 over the square root of mu naught epsilon naught, and you can check the units on this, it comes out to 3 times 10 to the 8 meters per second. That might be familiar. That's the speed of light, because this process of changing E fields producing changing B fields, which produce changing E fields over and over, propagating through space, is light.